Today on How It's Made. Decorative moldings. We give this topic wall-to-wall coverage. Commercial pulleys. Making the wheel that turns the belt in many machines. Industrial rubber hose. Not your garden variety hose. And sheet vinyl flooring. The lowdown on this laydown. When you consider the high cost of renovations, architectural moldings are an easy way to get a lot of decorative bang for your buck. By adding a crown molding along the ceiling, baseboard molding, casings, maybe even a chair rail molding, you can take a room from drab to dazzling without breaking the bank. Decorative moldings can be made of solid wood, medium-density fiberboard, or finger-jointed pine. These planks of eastern white pine are on their way to becoming finger-jointed molding. They've just come out of the kiln dryer. A hygrometer measures the humidity in each plank to ensure the wood is dry enough to cut cleanly. A worker directs a laser to read the dimensions of each and every plank. The laser transmits that information to a computer, which guides a plane further up the line to shave the plank to the required width and square it. This process transforms the plank into a block. The blocks now enter a high-tech piece of equipment that identifies defects for removal. As each block enters the machine, a scanner records all its features. It sends that information to a computer, which calculates a cutting plan. Guided by the computer, a saw chops out any knots or poor quality wood. The machine's kickers, as they're called, boot the cutoffs from the conveyor. The blocks, meanwhile, continue on, running against razor-sharp rotating heads that carve finger joints on the ends. The next station coats the joints with industrial-strength carpenter's glue. The conveyor picks up speed now and butts the blocks together with high pressure. The joints lock in a tight fit. When the glue dries, the joints strengthen even more. The jointed blocks are connected in a continuous unit. A saw now cuts it into standard molding lengths. These lengths are known as finger-jointed blanks because they haven't yet been shaped. A saw now cuts the blanks lengthwise to the thickness of the specific molding they're producing. The final step is to profile the blanks. A machine called a molder uses rotating steel knives to carve the wood to the required shape. There's a different knife for each style of molding. The molder transforms the blanks to moldings at a rate of 30 meters per minute. Moldings made of finger-jointed pine or medium-density fiberboard are the least expensive to buy. But you can't stain them as you can moldings made of solid wood. You have to paint them. A pulley is a wheel with a grooved or barreled rim in which you run a rope or belt. It's a simple device used to lift a load that's hard to access or too heavy to move by hand. Pulleys and multiple pulley systems are vital components of many types of machines. These pulleys are designed for use in small to large-scale electric motors. For example, fan belts in the air circulation systems of office buildings, factories, and mines. The factory makes its pulleys from a 50-50 mix of scrap iron and steel. The furnace heats the metal to 1,370 degrees Celsius, slightly above the metal's melting point. Workers adjust the chemical composition by adding carbon and silicon. The right recipe is essential for producing quality metal. In the furnace, the metal's impurities, called slag, rise to the surface. Workers use giant paddles to skim it off. Once the lab analyzes and approves a sample, they transfer the molten metal by ladle to a 30-ton holding furnace. This furnace maintains the metal at a constant 1,370 degrees Celsius, the required temperature for a proper casting. You can't pour metal this hot into a metal mold. The mold would just melt. So instead, the factory uses damp sand. Sand withstands intense heat by absorbing it. The machine forms the molds much the way you'd use a pail to form a sandcastle. It first constructs the bottom half of the mold. This filter will screen out any slag particles the molten metal may still contain, and these cores create empty spaces within a part. Now the machine forms the top half of the mold. They slip a weighted metal jacket around the finished sand mold. This keeps it from collapsing under the weight of the metal. Workers fill the molds right to the top. It takes from 30 to 45 minutes for the molten metal to solidify. They remove the weighted metal jacket, then dump the mold into what's called the shakeout. The vibration breaks the sand mold apart, releasing the metal pulleys. While the pulleys go off to be cleaned, the sand is recycled into new molds. The pulleys are in rough form. They still have to be machined to specifications. A robot places each one under a computerized camera. A visual recognition program guides the robot to position the pulley properly in the various automated tooling machines. The first machine makes the pulley's grooves. The next machine will drill holes in the hub for installing the screws. At the end of the machining process, a gauging system takes precise measurements and guides the equipment to correct any errors. This is a two-part pulley known as a variable pulley because it can run a belt at variable speeds. This tooling machine performs several operations on the male component. It machines the face and outside diameter on one side, then flips the pulley over to make the bore and threads on the other side. The last operation drills holes for two screws that will affix the pulley to the shaft of the electric motor. a touch of lubricant, and the next machine assembles the male and female parts. After setting the proper speed, the user locks the parts in position with a screw. Many industries use rubber hose in their day-to-day operations. Sometimes they use it to remove water or evacuate waste, or to supply certain machines in the factory with air or water or raw materials. For instance, food producers might feed ingredients through a rubber hose into a mixer. This company makes low-pressure and medium-pressure rubber hoses. The intended use is what determines the rubber composition. Function also determines the color, because industrial hoses are often color-coded. The rubber arrives at the factory from the supplier in rough strips. The first step is to run it through a mill. The rollers heat the rubber, softening and smoothing it to an even texture. The next machine cuts the rubber in strips to the precise width and thickness required for the size of hose they're going to construct. Workers lubricate a steel mandrel that's the exact size of the hose's bore. As the mandrel spins, they wrap a rubber strip around it, measuring and layering if necessary to build the thickness they're after. Next, they add one or more reinforcement layers. This strip is made of a high-strength synthetic fabric that's been coated in rubber. It's designed to withstand the pressure to which the hose will be subjected. The last layer of rubber forms the hose's outside covering. After verifying that the final diameter is correct, they wrap the entire hose construction tightly in wet nylon tape. The tape will later shrink and compress all the materials together. This factory also makes hoses with a built-in attachment on the end. They position it on the mandrel, then glue the first layer of rubber to it. Then they reinforce the bond with special textile strips and tightly wound high-strength carbon steel wire. They continue the wire, more loosely, down the body of the hose at a specific angle designed to withstand vacuum pressure. Then they wrap the hose in a soft, stretchy rubber strip that fills the gaps between the wires. Next comes a layer of high-strength rubber-coated fabric. Then finally, the exterior covering, light blue rubber for this model. They pressure wrap again with wet nylon tape. Then, to make the hose more flexible, they create corrugations by wrapping it tightly in rope. What's under the rope compacts, creating a dip. They add another layer of nylon tape to hold the rope in place. When construction is finished, the hoses on their respective mandrels go into an autoclave, a cylindrical chamber into which they feed hot steam at high pressure. This vulcanization process, as it's called, triggers a chemical reaction that cures the rubber, making it elastic. Once the hoses come out and cool, workers remove the shrunk tape. The layers are solidly compressed. They wash the nylon tape, then rewind and reuse it. Now workers begin the process of removing the hose from the mandrel. They tie one end with a rope to create pressure, then gently pump water between the mandrel and rubber. The lubricant they applied earlier has prevented the rubber from sticking to the steel, so the hose separates easily. They simply slide it off the mandrel. Workers will now trim the ends, cut the hose to the length the customer ordered, then coil and package the hose. This factory makes a wide range of industrial rubber hose in different outside diameters, different bore sizes, and varying degrees of flexibility. Some hoses have specialty features, such as heat-resistant fabrics incorporated right into the rubber layers. In 1860, an Englishman invented linoleum, a revolutionary floor covering made of linseed oil, pigments, pine rosin, and pine flour. A century later, in the 1960s, newfangled vinyl flooring walked all over linoleum and eventually rendered it obsolete. Vinyl flooring owes its existence to a German chemist who in 1872 invented polyvinyl chloride, or PVC. PVC was considered a thoroughly useless substance until the 1920s, when an American researcher tried to make it useful by turning it into an adhesive. He didn't succeed, but in the process, he accidentally discovered that heating PVC in a solvent transformed it into a flexible plastic, what we know today as vinyl. Sheet vinyl flooring comes in a wide range of designs, some of which simulate ceramic tiles or hardwood flooring. As we see here under a microscope, vinyl flooring is comprised of three components: a felt paper backing on the bottom, a layer of vinyl foam in the middle on which they print the design, and a protective layer of transparent vinyl on top. To create texture, the factory applies an inhibitor to prevent the foam from expanding in certain areas. To make that vinyl foam, they first mix the powdered ingredients: polyvinyl chloride resins, or PVC, white pigment, and calcium carbonate, which acts as a filler but also helps color the mixture white. In a separate mixer, the liquid ingredients: plasticizer to make the vinyl flexible, fungicide to prevent mold growth, UV stabilizers to prevent fading, and a blowing agent which they later activate to inflate the foam. They combine the liquid and powders and mix for another 15 minutes. After filtering the mixture to remove any lumps or paper bag fragments, the liquid foam goes to the production line. There, a large coater applies an even layer to a continuous sheet of felt paper backing. The coated backing then passes through an oven for about 15 seconds. The heat, 220 degrees Celsius, solidifies the liquid foam, fusing the PVC and adhering it to the backing. At this point, it's critical not to activate the blowing agent. The floor's design will be printed directly on this foam surface. A graphic designer creates the artwork by computer, then with a colorist experiments with dozens of color combinations before deciding on which ones to use. The computer breaks down the final design by color in order to produce an engraved plate for each one. Then they test out the design on a piece of foam, printing one color after another until the design is complete. On the production line, printing works the same way. But because it's a continuous process, they use rotating cylinders rather than engraved plates. The flooring just rolls right through them, receiving up to 6 ink colors one at a time. A dryer dries the ink in between applications. It's time to apply the floor's top layer. This coat of vinyl is known as the wear layer because it'll be subjected to the wear and tear of walking. The wear layer protects the design printed on the vinyl foam underneath. Made of PVC resins and plasticizer, it goes on white but turns transparent once fused in the oven at 220 degrees Celsius. At the same time, the heat of the oven activates the blowing agent in the vinyl foam underneath, expanding it. To create texture, they use a process called chemical embossing, in which select ink colors contain a chemical inhibitor to suppress foam expansion. Wherever they print those colors, the foam remains flat. These height variations create relief and can simulate grout lines in imitation tile designs. To give the surface a sharper, more natural look, the flooring can proceed to a second process called mechanical embossing, in which an engraved roller imprints its pattern onto the surface. The gloss level of the flooring, meanwhile, varies with the chemical composition of the wear layer. Workers inspect the finished flooring as it rolls off the production line. It's 3.7 meters in width, wide enough for seamless installation in most rooms. The packaging is entirely automated. The equipment winds 30 meters of sheet vinyl flooring per roll. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.